Hi, everybody. I am Sean Smuckler. I'm an associate professor in the Faculty of Land and Food Systems at the University of British Columbia, and I'm the chair of Agriculture and Environment, a position that's partly funded by the BC Ministry of Agriculture, Food and Fisheries to provide actionable research to the farmers of this province. I also lead the Sustainable Agricultural Landscapes Lab. We'll call it the SAL Lab. So I also would like to begin by acknowledging that I'm speaking to you from UBC, the UBC Vancouver campus, which is on the traditional, ancestral, and unceded territory of the Musqueam people. And I know folks from on this call are calling from all different spots in the province and maybe beyond. So I'd implore you to just take a minute to think about where you're calling from, the history of the land that you're on. Today we're going to be sharing results from studies that were carried out by the SAL Lab, and also providing farmers with some opportunity to discuss some various management options for dealing with what I think is probably one of the most pressing issues of our time, dealing with the impacts of climate change. I do want to thank the farmers that participated in this research from the get-go. We had more than 15 farmers that participated in the research that will be presented, and really wouldn't be possible without them. Their farms served as trial sites across southern BC, and we are very grateful to be able to utilize their land, which also sits on the traditional and ancestral and unceded territory of a number of First Nations. So funding for this research was provided by the Climate and Agriculture Initiatives Farm Adaptation Innovator Program and the Natural Sciences and Engineering Research Council of Canada. Just a quick intro to what the SAL Lab does. The SAL Lab works to understand the trade-offs and synergies of various agricultural management options to produce research with tangible outcomes for producers and policymakers. We're really trying to help farmers identify management practices that they can adopt to improve the profitability and the sustainability of their farms. Here in BC, we don't have a formal extension program, so our lab really strives to engage with farmers to co-develop research that's going to be most useful and help fill that gap. To enhance the relevance of our research, we focus on doing our projects in collaboration on farm and making sure that we get back to farmers with the results from the projects that we're working on. Workshops like this really help us share our findings, but also enable us to get feedback from you and some input on your interpretation of the results, and be able to share with us some of your experiences. So we're hoping to hear what you think of the research, and also to help us put it into context and to hear about what you would like to see us work on next. So yeah, I'm really looking forward to the breakout rooms and hearing about what farmers have to say about the management strategies that we're going to be focusing on today. And then, yeah, just a final note, the SAL Lab is also aiming to train people to provide support and leadership for our agricultural sector. So you're going to hear from several of those people today. Yeah, and finally, funding for this workshop has been provided in part by the Government of Canada and British Columbia under the Canadian Agricultural Partnership, a federal, provincial, territorial initiative. So if we switch to the agenda, yeah, so our agenda today, we'll be doing research presentations, provide some time for question and answers. We'll have a break. Our first, during that break, I would encourage you to maybe go grab some food, and you can eat lunch while we're in our discussion group. So after the break, we'll do discussion groups and then a final plenary session and wrap up by 1 o'clock.
So with that, I'm happy to be kicking us off this morning. with the first of 2 research presentations sharing some of the results from on-farm field trials that we conducted in BC. Specifically, this project looked at the impact of overwinter soil cover on soil properties in the following spring. This project was supervised by Dr. Sean Smuckler, who you've met already this morning. He's the principal investigator of SAL Lab, and this project was also conducted under the leadership of Dr. Kira Borden, who you will hear from in the second research presentation. And again, my name is Raylani. I'm a Master's of Soil Science student with SAL Lab. To give you an idea of how this presentation will flow, I'll start with project background, project design, talk about how we collected our data and the key findings. I want to first recognize that this project took place on the traditional and unceded Indigenous territories within the colonial borders of BC, as Sean mentioned previously. And as with much of the work in our lab, climate change and conversations with growers are the impetus for this work. Many of the soil management challenges facing BC growers stem from the shifting precipitation patterns that we're seeing. So it's predicted that spring and fall precipitation are going to continue to increase. We're getting more rain during these times, which you may have already experienced after the atmospheric rivers and flooding in the fall of 2021. One consequence of this rain is that it decreases soil workability and trafficability during the shoulder seasons, meaning that wetter soils make it more difficult to use equipment in the field, and the negative impacts to soil health that we can see from tillage may be worsened in these wet conditions. And as many of you know already from your firsthand experience, the shoulder seasons are critical for the establishment and termination of winter cover crops, especially for vegetable and annual growers. But the timing of this tillage and cover crop establishment can be made more complicated by wet soils. Often the ground is tilled prior to seeding cover crop, and in the fall, the ground is tilled in the fall prior to seeding cover crop, and then again in the spring to terminate the cover crop. And Kira is going to dive more into the subject of cover crops in the next talk, so I'll keep this part brief. And many of you know already who grow cover crops that there are many benefits. Winter cover crops are important soil health. It's an important soil health practice because they provide soil cover. They can increase species diversity and maintain living roots in the soil over the winter. Cover crops can also facilitate nutrient, especially nitrogen cycling, and protect residual nutrients from leaching in winter rains. However, there's certainly some trade-offs and tensions when we're using cover crops, especially when we think about getting them established across an entire farmscape on a highly diversified farm, as many of your mixed vegetable and flower operations tend to be. So in addition to other challenges, these wetter conditions we're experiencing make the timing of establishment and termination difficult, especially for late season crops that don't come out of the field in time for the robust establishment of a cover crop going into the winter. So one alternative strategy that's been gaining in popularity amongst growers is the use of silage tarps. And silage tarps are impermeable, black on white UV treated polyethylene. These tarps can be used as an alternative soil cover or in conjunction with cover crops to reduce spring and fall tillage. But we don't have a lot of information on the impact of these tarps as it relates to soil properties or crop yield. And that information would be helpful for growers to evaluate the trade-offs between overwinter cover strategies. So with this in mind, we developed our central research question, which was, what are the impacts of overwinter soil cover type on soil properties? And we focused on 2 strategies, cover crops and silage tarps. To investigate this question, we set up a 2-year on-farm trial beginning in the fall of 2019 and concluding in the fall of 2021. To collect a robust set of data, we conducted 2 different experiments, the first being an experimental study, which we implemented on 2 farms, and then the regional study, which was conducted on 12 farms. And you can see their locations on this map. All of the farms are concentrated in 3 agricultural regions. So we have Vancouver Island, the Lower Fraser Valley, and the Kootenay Mountains. So the experimental sites were located, one in Vancouver at UBC Farm and the other in the Cowichan Valley on Vancouver Island at Greenfire Farm. So Greenfire Farm is owned and operated by Delisa Lewis, who is with us today and may be a familiar name to many of you. She not only helped manage the research on her farm, but also was instrumental in developing and carrying out this project on Vancouver Island. I'd also like to note here the work of Carson Lee and Kira Borden at UBC Farm. They did a lot of work on that trial. So the hallmark of this experimental trial was that we were able to conduct a more controlled and managed experiment than on the regional farms. So the overwinter treatments were replicated in the experimental trial. There were 16 tarp and 16 cover crop plots on each farm. And you can see that in this picture. This is Greenfire. And this replication helps to make the data more robust because there are a greater number of samples we're collecting from each farm. And this can help us weed out any anomalies or aberrations that we might see. And we're also able to control other management factors like fertility applications and irrigation type on these farms, which allows us to paint a clearer picture of the impact of overwinter treatments. These 2 farms also have very different soil textures. UBC Farm is a coarse loamy sand, and Greenfire is a finer clay loam. Now, in the regional trial, different from the experimental trial, we had just 1 tarp and 1 no tarp plot on each participating farm. So we didn't have on-farm replication in this trial. And an important difference here as well is that on the regional farms, we consider the comparison between tarp and no tarp, as not everyone was able to establish a cover crop. The regional study allowed us to look at some of the impacts of these tarps across a wide variety of climates and soil types, and gather input from a variety of farmers who are using these techniques. So these are some examples of our regional sites. You can see in the bottom left here, this farm did have a cover crop, whereas in the middle here, we have our tarp plot, and then there's crop residue on the bed next to it, and that's our no tarp plot. And then in some cases, there was a bare fallow. So we sampled the soil at the time of tarp removal in the spring of 2020 and 2021. So these are the springs after the overwinter soil cover treatment. And we measured soil water content at a depth of 0 to 8 centimeters. And then we sampled the soil at a depth of 0 to 15 centimeters to measure both plant available nitrogen and electrical conductivity. So these samples taken at the time of tarp removal, but the tarps were removed on a farm by farm basis. So the growers chose the date depending on the crop they were going to grow and other logistical constraints. So in this trial, the tarps were removed between March 29th and May 3rd of both years, with the average date being April 15th. And at UBC Farm, we were able to collect more data over the winter, especially when it came to soil water content, which is the first of the results that I'll talk about. So soil water content is an important indicator of soil workability, which we talked about at the beginning. And we were interested in how these tarps would influence water dynamics and if they would create drier spring conditions. However, the spring soil moisture data collected from our trial didn't show a clear trend. In general, the tarped ground was wetter in the spring than the no tarp or cover crop areas, but this wasn't consistently true. So we looked to the data from UBC Farm to help us figure out what might be going on. At UBC Farm, we were able to take soil water measurements approximately every 2 weeks throughout the entire 2-year trial. So this is a timeline of soil water content at UBC Farm, and we have the months of the year down here on the x-axis, and we're starting in November of 2019 all the way through October of 2021. The gray shaded regions on the figure represent the times when the tarps were installed in the field. And on the y-axis, we have soil water content measured as volumetric water content. And then we have the green dots and lines representing the cover crop plots, and then the black triangles and lines representing the tarped plots. So if we start at the beginning, we put the tarps on, and when we installed these tarps and planted the cover crops, the soil moisture appeared the same in all of our plots. But after a few weeks, the tarp ground starts to, it's drier than the cover crop ground, and it stays that way for December and January, February, into March. And then in about mid-March, we see that the cover crop starts to dry out. The moisture starts to drop, whereas in the tarp plots, the soil moisture holds pretty steady until we remove the tarp and soil moisture starts to converge. The growing season happens here. We don't see visual differences in soil water by treatment. And then we put the tarps back on for our second year of the trial, and we see something similar happen. So after a few weeks, the tarped ground appears drier. For the most part, stays that way throughout the winter until this time in mid-March. You can see inside the red circles for both years. So from this information, we can see that the timing of tarp removal is likely to be very important to soil moisture. And the amount of water in the soil and the exact timing of this is going to be related to the soil texture. So again, this is UBC Farms, a very coarse textured soil. And it'll also be related to the amount of precipitation. So we would expect that the timing and trend of this would change region to region and farm to farm. So the next key finding is about nitrate levels. So nitrate is a form of plant available nitrogen. And as growers, you know that meeting crop nitrogen requirements is important for both yield and plant health. But an excess of soil nitrogen represents an environmental concern. So we were interested in measuring nitrate in this study because we predicted or thought that these tarps may help protect residual nitrogen left over in the soil from the growing season, protect that nitrate from leaching, because these tarps aren't allowing much rain to infiltrate and percolate through the soil profile, which is how nitrate would be moved. So when we measured nitrate, we did see a consistent story here. There were elevated levels of nitrate in the soil under the tarps compared with the no tarp and cover crop plots. So I'll show you a figure of what we found, and let's walk through this together. So on the x-axis, Here we see the farm sites and region. So UBC farm on the left, Greenfire in the middle, and then these are each of the regions of the regional trial. So Kootenay Mountain, Lower Fraser Valley, and Vancouver Island. The data is also divided by year. So there's the data from 2020 on the top and the data from 2021 on the bottom. And as with the last figure, the green points are cover crop or no tarp, and the black triangles are tarp data. So we can see here across the board that nitrate is higher in these tarped areas. And at UBC Farm and Greenfire Farm, we would certainly expect this because the cover crops are likely took up a lot of this residual nitrogen from the soil. But in the regional trial, where there weren't consistent stands of cover crop, we still see this difference in nitrate. And when we contextualize the amount of nitrate underneath these tarps in the spring, we thought about it in terms of the fertility requirements for a subsequent crop. And the observed nitrate levels under the tarps represent an agronomically sizable amount of nitrogen. So we grew beets at the experimental farms in the first year of study. So I'll use this crop as an example. At the higher range of our nitrate observations, the levels we saw would represent more than 70% of the recommended nitrogen application rate for a beet crop in BC. It's important to keep in mind, though, that the amount of nitrate measured in the spring would be related to the fertility application rate in the previous growing season, and then also how much is left over in the soil after crop harvest. So this will vary farm to farm depending on fertility management. And then from a management perspective, we can also think about the different ways to harness this under tarp nitrogen. The timing and amount of rainfall between tarp removal and planting of a cash crop may influence the nitrate that's available for plants. So we could think about reducing the time from tarp removal to planting. Also, the density and modality of planting will impact the capture of nitrate by plants. So transplants with developed root systems may be better able to utilize this residual nitrogen more quickly than a direct seeded crop. The last measurement I'll discuss today is electrical conductivity, or EC. So soil EC is a measure of soil salinity, or the amount of salts in soil. And this isn't table salts. This is salts are charged particles or ions that are floating around in the soil. So often these salts or ions are important plant nutrients, and nitrate is just one example. And EC is an important indicator of soil health. So it affects crop yield and plant nutrient availability. And given the elevated nitrate we observed under the tarps, we wondered if the tarps were potentially protecting other ions from leaching. And we were also curious to see if the soil salinity would build up from the first year to the second year of the study. And we can see this happen with the use of different types of plasticulture that exclude rainfall, like high tunnels or greenhouses. Okay, so similar to our observations of nitrate, we saw that tarped plots had higher electrical conductivity than the no tarp plots. And this measurement doesn't tell us which types of ions are in the soil, but it does tell us that they're there. And we didn't observe an increase in soil salinity from 2020 to 2021, indicating that we didn't build up soil salts during this trial. And an electrical conductivity reading or measurement of 1 decisiemens per meter or greater is considered detrimental to plant growth. And all of the measures of electrical conductivity in this trial were below that threshold. Okay, so from the results of the study, it seems that silage tarps are certainly a promising tool for some overwinter applications. We observed that the timing of tarp removal was really important in influencing soil water outcomes, and we posit some soil nutrient outcomes as well. It's also important to acknowledge that this is just a 2-year study, so we can't speak to the long-term impacts of these tarps. We would expect there to be impacts to soil organic carbon if the tarps were used in lieu of cover crops for extended periods of time. And there could also be impacts to soil salinity. And if you want to know more about this project, we'll have a final report up on our website, and you'll receive a link to this in a follow-up email. There's also an episode of the Organic BC podcast where we talk more about this project, and you can hear from some of the participating farmers. And then if you're a farmer interested in collaborating with Sal Lab, you can always reach out to myself or Sean by email. And Sean is going to talk a little bit about the upcoming research that we have building on this project, and that'll happen after Kira's presentation. So stay tuned for more information there. And certainly so many people worked on this project almost exclusively during a pandemic. So big thank you to everyone who contributed. And yeah, again, a special thanks and shout out to the collaborating farmers. None of this would happen without you.
Thanks, Raylani. It's exciting to see those results. Okay. And Raylani, could you just turn your video on and thumbs up if you can see the screen okay? All right. Okay, hi everyone. Thanks again for having me join into this workshop series. I met some of you last week if you were at the nutrient management session. I'm Kira, and I worked at UBC as a postdoc researcher with Sean in the Sustainable Agricultural Landscapes Lab. And yes, so last week I talked about some of the work that we did with regards to nutrient management. I also worked with Raylani on the overwinter experiments that she just talked about. And we were talking about how we could, what could we add to this series, and maybe just dive a little bit more into the cover crop side. So this, I'm not going to talk about a specific study. So hopefully it doesn't sound a little too hodgepodge, but we're going to show you some information that we gleaned from our cover crop data over the course of the last 4 years of these experiments. So from the overwinter trials, as well as our nutrient management work that we did, and we talked about it last week. If you weren't in last week's session, that's okay. I'll give some background as needed through this talk. Okay, so here are some images of UBC farm, kind of in the same direction of the field actually. So we've got the tarps and the cover crops. This would have been following the season in 2019. And then the subsequent tilling in of the cover crops in preparation for growing the growing season. So, Raylani talked about a lot of the benefits that come from cover crops, and then specifically dived into evaluating the impacts on some key soil parameters that could change over the course of the winter, and in response to trying to adapt to a changing climate. But what I'm going to show you is just the piece of the nutrient budget side. So this could help, build a bigger picture around, Raylani talked about the implications for nitrates when you tarp. But what about the nitrogen that comes from cover crops? So if you decide not to plant cover crops, what are the implications for your nutrient budgets on the farm? Or if you are cover cropping, how does that scale in terms of your farming practices. So this is a very basic 101 of cover crops and nutrient management, just to get everyone on the same page. So we've got your summer crop and then the winter going into next summer. Of course, if you don't have any plants in place, those roots that are in the soil, then you have a risk of losing soil nutrients over winter, especially if you're in a high precipitation zone, which many of you are. So we grow these cover crops or catch crops to effectively catch nutrients in the soil and hold them in place and return them back into soil when we reincorporate them in the soil for the next crop. We can also add nitrogen to the system with nitrogen fixers. So this is via those associations that some plants can have with microbes to get nitrogen out of the atmosphere and bring it into the plant rather than taking up nitrogen from the soil. So you're adding nitrogen to the system. The data of what the nutrient composition of our cover crops was. This is a very hard cover crop in the spring of 2019. So we've cut down and weighed the cover crops in a certain area so we can extrapolate to a larger area. Raylani, I just had a little warning that says my internet is unstable. So if it's getting glitchy, can you just let me know?
Yeah, it was a small lag, but we still heard you.
Okay, great. So within that little area, and we do this in multiple locations across our plots, we get the weights of how much biomass is there, and then we analyze those plants for the composition of nitrogen, phosphorus, and carbon. This is just some data from 2020, get a sense of how much nitrogen and phosphorus is there. In terms of nitrogen, about 25 kilograms of nitrogen per hectare, which back of the envelope calculation, I hope I got this right. For farmers, that's half a pound of nitrogen across a 1,000-foot square field. And for phosphorus, it's 4 kilograms of phosphorus per hectare, or 0.1 pounds of phosphorus in a field size. We're also adding carbon. Of course, the plants are photosynthesizing and sequestering carbon into their biomass, and that's getting incorporated into the soil. So we're adding upwards of 400 kilograms of carbon per hectare with cover crops. And I also want to add that this is for above ground plant material only, where we did not account for what's going on below ground. And if some of you know me well enough to know that I'm obsessed with roots, so we're missing out a big component of what we're adding to the soil or keeping in the soil. So just keeping that in mind when we look at these numbers. So what does that mean if we're thinking about the overall nutrient budgets of a farm or a small scale vegetable farm in this case? So these values are coming from our research farms at UBC Farm and Greenfire. And I just thought it would be interesting for some of us just to get a sense of that scale of what's in the pools of nitrogen and phosphorus in cover crops versus what we're adding to the farms versus what ends up in the crops in the end and those crop demands. And what we see is that, yeah, cover crops, depending on the crop, depending on what we're applying, of course, so this is all context dependent, can be a substantial portion of that total pool that moves through the system or gets added to the system. Or it could be a bit diluted if you're adding a lot of compost, for example. So I'm not going to dwell too much on these numbers because it's going to be very context specific, but I think the main point here is that, of course, cover crops are non-negligible in these organic vegetable systems when it comes to the overall nutrient budgets of the system. Now, one little caveat, or I guess interesting tidbit that came out of it, and someone actually asked a question relating to this last week, is if, are we seeing any legacy effects of some of the other management practices that we're trialing on our cover crops? And one, big management practice that we're trialing is the use of compost and organic fertilizers. So trying to dial in more effective nutrient balance on farms. And so that's what I talked about and Amy talked about last week. And we see that in these plots, there's actually a knock-on effect or a legacy effect on our cover crop biomass, which is quite interesting. And specifically, so along the bottom, we've got these different types of organic amendment treatments that we were trialing out. So whether we've added nothing to lots of compost, to moderate amounts, to low amounts with a little bit of fertilizer, we see a very strong response in terms of the subsequent cover crop biomass. So in those high compost plots. So there's an interesting temporal and dynamic story that gets played out between the management side of nutrients of what we're adding in amendments and subsequent cover crop growth, and then the return of nutrients from those cover crops. And the last little tidbit that we've gleaned from our from our cover crop data is in regards to species composition. So, as a farmer, you might be wondering which cover crops should I plant. And from the polls, I saw that a lot of you are planting a range of different species. So you probably have lots of much more applied intel on what works for your farm. But different species obviously have different benefits and from one another. So you could have a certain type of grass that really grows quite well and produces a lot of biomass versus a nitrogen fixer like the clover in the middle that are adding nitrogen to the system and also have a lower carbon to nitrogen ratio in their tissue. So they decompose and release nutrients differently. So there's a big push to, and then the last image is a mixture of different species. So there's lots of emphasis on diversification of plants on farms. And one way to do that beyond just cover cropping is mixing the species of cover crops and doing so to try and optimize, the benefits from different types of species. So this work is being conducted in many different places. But from some of the data that we've gotten from our work, we measured the species composition of these mixes on our research plots. So we weigh out the different amounts of the different species of, for example, clover, rye, and pea, which are the three mixes or the three species in our mixes that we're at UBC and Greenfire. So I'll just show you some quick data to start, I guess, thinking about how this could impact a farm and how it could also inform future research. So the graph here shows how much cover crop dry weight biomass is at the farm. UBC has, full disclosure, so Greenfire Farm seems quite low in contrast to UBC Farm. That's because we forced Elisa to be on the schedule that we need her to for our research trials. So I think we really pushed late into the fall for cover crop establishment on her farm on Vancouver Island. And so thank you, Delisa, for being so accommodating. But with this, we do get some interesting information when we look at what actually established and made it to the spring when we sampled the cover crop before it got reincorporated. And we see that, so this is starting from the same species mix seed, we end up with a higher proportion of nitrogen fixers at UBC Farm versus at Greenfire Farm. And there could be many different reasons that cause this difference. But, considering that these nitrogen fixers can actually add upwards of, they can derive 80 to 90% of their nitrogen from the atmosphere. That's a substantial amount of added nitrogen to a system that these nitrogen fixers can bring. So these proportions of nitrogen fixers versus the non-nitrogen fixers are something that's important to consider, and how that can get impacted by different establishment challenges. Okay, so there's hopefully those are just like little snapshots of some of the data that we've pulled in from our various experiments. But moving forward, I know that Sean has a cover cropping experiment on the go. So focusing a lot more on cover crops in terms of full research questions, as well as I'm working in cover crop systems here in Ontario. So some important questions coming out about spring management and the subsequent impacts on soils and crops. And cover crop establishment, shifting climate. So these are themes that Raylani also touched on. The performance of cover crop mixtures. And there's a lot of, excuse me, a lot of gaining interest in the impact of cover crops on, or how cover crops can play a role in climate change mitigation. So whether that be through increasing soil carbon or reducing nitrous oxide, and methane emissions from the soil, so your greenhouse gas emissions. And lots of other questions, I'm sure, which we hope to hear from during these breakout groups and Q&As.